Hi everyone, welcome to week 14 for higher level junior cycle. Today we're going to be looking at counting and probability. So we're going to be going through some theory, and then we're going to be looking at some exam questions as well. So we're going to be looking at the fundamental principle of counting first. So when we talk about the fundamental principle of counting, it refers to the total number of possible combinations from a set of groups. For example, suppose a restaurant has two options for starters. So we have soup and salad, there are your two options. And then four options for mains, which are beef, chicken, fish and vegetarian. So we can then work out by hand how many combinations between the two groups manually. So I'm just going to write out here again. So starters, we have two options. So we have soup and we have salad. And then for mains, what they've told us is that we have four options. We have beef, chicken, fish, or vegetarian. So you've got four options for mains and two options for starters. Now we can work out by hand how many total combinations between the two groups manually. So if we look at the selection here, first is soup and beef, second is soup and chicken, soup and fish, soup and vegetarian. Then we have salad and beef, salad and chicken, salad and fish, or salad and vegetarian. So we can see that there are 8 options, but the way we worked this out is that we see that there were 2 options for starter and 4 options for the main. So the total number of possibilities is 2 by 4. So again, we can see with starters, we have 2 options here, and for the mains, we have 4 options. So the total number of options is your 2 starters multiplied by your 4 main courses. That's 8 different possible combinations, and you can see the 8 combinations written in the above table. So the next thing we're going to look at is the likelihood scale. So I'm just going to scroll down here. So probability is the mathematics of likelihood. So that's measuring how certain or how uncertain an event is. For example, if you flip a coin, the outcome is not always the same. The likelihood scale is an informal way of describing events and outcomes in words rather than numbers. And I'm just going to underline that so you're outlining it in words rather than in numbers. So an example here, for each of the statements, describe how likely this event, that should be, this event is to happen. And you draw the likelihood scale to represent this. So if we look at the first example there, A, so what is the likelihood that the sun will rise tomorrow? Now that is certain, that the sun will always rise. So we have marked it into certain here on the probability scale. Now you can see there they put even in the middle, which would make sense, and then impossible is at the other end of the scale. So we've impossible, even, and then certain. So if we look at B, I roll a standard 6-sided die and get a 7. So this event is impossible. Now it must be impossible because there's no such thing as rolling a 7 on the die. So you can see that B is down as impossible. If we look at C, I flip a coin and get a head. This event is as likely as the alternative as getting a tail. So this is even because you've only 2 possibilities. Either you get a head or you get a tail. So for C, we place it at even. If we look at D, what is the possibility or the likelihood that it will snow in Dublin Airport next year on December 25th? So this event is possible, but looking at the weather from previous years, it is unlikely. So they place D somewhere between even and impossible, but it's more so leaning towards impossible, but it still is possible. So we place it where we've placed it. And then we look at E. What is the probability that it will rain somewhere in Ireland next year on December 25th? So this event is likely given the weather in Ireland. It's not certain, but it's likely. So we place it just here. So that's the probability scale, the likelihood scale, sorry. And we use the likelihood scale to show how likely an event is to occur. So I'm going to scroll down here now. And this time we're looking at experiments, outcomes and events. So we will use the following example of rolling a 6-sided die to define some terminology for probability. So the experiment is just to roll a 6-sided die itself. The outcomes are the 6 sides. We call the sample space. So I'm just going to underline this, and the outcomes are the 6 sides. So you get 1, 2, 3, 4, 5, or 6. And then the experiment is the rolling of the die itself. So the sample space is the collection of all possible outcomes. So in this case, this is your sample space here. They're all of the possible outcomes. Either you roll 1, 2, 3, 4, 5, or 6. And then finally, an event is a subset of the sample space. So the event, maybe rolling a 6, an event of rolling a 4. So here are some examples of events and the corresponding subset of the sample space. So rolling a 6, the subset is 6 because you can see 6 is in the original sample space, which is here. So the subset 6 is written like the first bullet point there. What is the probability of rolling an even number? So the subset of this is 2, 4, and 6. They're all the possible even numbers that you can have on a die. Rolling a number greater than 6, so this is empty, as you can see here, and it's empty because there is no number greater than 6, so that's the empty set. Then rolling a number less than 7, well, that's going to contain all of the numbers 1, 2, 3, 4, 5, and 6, and that's the whole sample space. So that's just some terminology that we use for probability, and the keywords there to remember are experiment, outcomes, sample space, and event. So the probability scale is the last part of theory we're going to look at before we go to questions. So probability is a mathematical representation of the likelihood scale, so how likely something is to happen. For each event, we can come up with a number between 0 and 1 to represent how likely we think that that event is to occur. The probability of a 0 means that the event is impossible, and the probability of 1 means that the event is certain. So I'm just going to write this up here. 0 means that the event is impossible. So something like rolling a 7 on a die, and if you get a 1, that means that the event is certain. And usually the probability lies somewhere between 0 and 1, depending on what it is. So in practical terms, if we repeated an experiment a large number of times, we'll say n number of times, we can count the number of times a particular event occurs, f for the frequency. Then the probability is given by f over n. For example, suppose we have a coin and our event is getting a heads. If we flip the coin 100 times and count 53 heads, the overall probability of getting a heads is 53 out of 100, and that's 0.5. If we let h represent the event that a coin is heads, then we write the probability of h as ph is equal to 0.53. So what that means is the probability of rolling a heads is 0.53. And the way they got that was in the experiment, flipping the coin 100 times, so it's out of 100, they actually rolled heads 53 times, and when you put that into the calculator you get 0.5. So that's where this came from. So we're going to do some examples now from exam papers. So the first exam paper I have here is the 2014 paper 2. So Pauline flips a fair coin 3 times. Now what fair means is even chance of landing on a head or a tail. So Pauline flips a fair coin 3 times and records the outcomes. She writes H for each head and T for each tail. Complete the table below to show all of the possible outcomes, and 2 of the outcomes have already been filled in for you. So there are 8 possible outcomes. You have to write all of the possibilities there are. So the first one there is 3 heads. The next one is 2 heads and a tail. Another option would be a head followed by a tail followed by a head. Another one would be a head followed by a tail followed by a tail. So they're all the possibilities starting with a head. So then I'm going to go with the possibilities starting with a T. So tail, heads, heads would be an option. Tail, heads, tail would be another option. Tail, tail, heads would be another option, and then finally rolling 3 tails. And you just have to think about these, and it's handy when it's giving you a table like that, because it's a hint that there are only 8 possibilities. So the first question there, find the probability of getting 2 heads and 1 tail. So 2 heads and 1 tail. So how many options can we count in the table there where we have 2 heads and 1 tail? So if we look, so 2 heads and 1 tail, that's one option. 2 heads and 1 tail, that's another option, and 2 heads and 1 tail. So that's 3 I see there. So that's going to be 3 out of the total, which is 8, because we have 8 combinations. Now, if we wanted to write that properly, the probability of getting 2 heads and 1 tail equals 3/8. Okay, so we're going to go to the next question. Jamie says, you have the same probability of getting 3 heads as you do of getting 2 heads and 1 tail. Do you agree with Jamie? And give a reason for your answer. Well, if we look back up at the table here, what is the probability of getting 3 heads? The probability of getting 3 heads, it's only this option here, so that's only going to be 1 out of 8. Whereas the previous answer, the probability of getting 2 heads and 1 tail, we found out was 3 out of 8. So the answer there is that no, we wouldn't agree with Jamie. And the reason is the probability of actually rolling 3 heads is 1 out of 8, which I've highlighted in green above. That's only one combination. But the probability that we worked out before of getting 2 heads and 1 tail is 3 out of 8. So we worked that out already. So that shows that Jamie is incorrect. So then let's go down to the last question. Max says you have the same probability of getting 3 heads as you do of getting head followed by tail followed by head. Do you agree with Max? Give a reason for your answer. Okay, we know that the probability of getting 3 heads is 1 out of 8. But the probability of getting this specific combination, head followed by tail followed by head, let's go back up and see. So head followed by tail followed by head, that's this option here. And I don't see that option anywhere else, which means that that is 1 out of 8 as well. So we would agree with Max. So the reason being is the probability of rolling 3 heads was 1 out of 8, which we've already looked at. And also the probability of rolling head followed by tail followed by head is also 1 out of 8. And I'm just going to go back just to explain that again. Head followed by tail followed by head is this option here. There's only one of those combinations, and there's only one of these combinations as well, which proves that Max is correct. So that's the answer to that question. We're going to go on to the next paper now. So we are going to go on to the next paper now. So let's zoom out a bit. So this is 2014 and it's the sample paper, and it's paper 2, question 3. So John is going to a festival for the weekend. Each outfit he will wear consists of a pair of jeans, a shirt, a jumper and a pair of shoes. So what he has packed is 3 pairs of jeans, which are black, navy and blue, 4 shirts, which are white, green, yellow and red, 2 jumpers, which are black and brown, and 3 pairs of shoes, which are boots, sandals and flip-flops. So what we have to do is write down 2 examples of different outfits that John could select to wear. So you can literally pick any combination at all, as long as you have a pair of jeans, a shirt, a jumper and a pair of shoes. So I'm just going to do an example here. So we'll say navy jeans, white shirt, black jumper and boots. And I'm going to change back to my blue pen here because I should have it in blue. And another example, we'll go with black jeans this time. Now again, you can pick any combination. So black jeans, green shirt, we'll say this time. We'll go brown jumper. And sandals. So that's 2 examples of different outfits that John could select to wear. How many different possible outfits could John wear over the weekend? So how many pairs of jeans do we have? We have 3 possibilities. So it's going to be 3 multiplied by how many different possibilities we have of shirts? We have 4. How many different possibilities of jumpers do we have? We have 2. And finally, how many different possibilities of pairs of shoes? We have 3. So I'm multiplying 3 by 4 by 2 by 3, and you put that straight into the calculator and you will get 72 possible outfits. And that's the answer to that one. So the next paper I have is 2015, paper 2, question 2. Now you'll see a lot of this in exam papers. So a restaurant menu. So below is a menu from a restaurant. We have a 3-course dinner which is made up of 1 starter, 1 main course and 1 dessert. Now if we look at the starters, there's soup, garlic bread, onion rings or chowders. We have 4 options from the starters. For the main course you can pick pizza, spaghetti, steak, lamb or salmon. So there are 5 options to pick from the main course. And then finally dessert, there's cheesecake, chocolate cake or ice cream. So that's 3 options. So just keep that in mind. Now it says to calculate the number of different 3-course dinners that can be ordered from this menu. So this is going to be the total amount of starters, which is 4, multiplied by the total amount of choices for main course, which is 5, multiplied by the total amount of dessert choices we have, which is 3. So we're going to multiply those together and you get 60 different 3-course dinners. So that's the answer to part A. So we're going to look at the next part now. In a restaurant, there is a circular poster for each course where the options are represented by sectors of equal area. So the poster for the starter is shown on the diagram on the right. So calculate the angle of each sector in the main course poster and each sector in the dessert poster. So construct these sectors in the diagrams on the next page. Okay, so we're going to do the calculations first. Now, with the main course, there is 5 options. Now, in a circle, we have 360 degrees. So for the main course, for the main course angle, so we're kind of bringing in a bit of geometry into this as well. So main course angles, so the total amount of degrees in a circle is 360. And we're going to divide that by the total number of options for main course we have, which is 5. And that's going to give us 72 degrees. So each sector, or each angle in the sector for the course for main course, for the sector on main courses should be 72 degrees. Now if we want to look at dessert angles, so remember we only have 3 options for dessert, so we have a total of 360 degrees in a circle, and we're going to divide by the total amount of dessert options we have, which is 3. 360 divided by 3 is 120 degrees. So each of the angles for the desserts should be 120 degrees. So if we scroll down, we've been given actually 2 circles here, and you use your protractor here to calculate the angles properly. Now I'm using a tablet, so mine won't be as accurate as yours is, but you use a protractor and you measure the angles correctly. So I'm just going to draw roughly what it should look like, but again you're going to be using your protractor. So that's your first line, and this is going to be your second line here, and then we're going to have our third line roughly there. So that's dessert, and each of those angles, remember, are 120 degrees. So I'll actually just mark that in. So that's 120. This is 120. And then this is 120. So you use your protractor for that. Now the main course, so this is 5 sectors. So this is going to be harder for me to draw, but I'll give it a go. So we're going to split this into 5 sections. And each of them should be 72 degrees. So that's the first one. Second one, third one, the fourth one, and the fifth one. So each of those will be 72 degrees. So 72, 72, 72, 72, and finally 72. Okay, so we're going to go to the next question now. The owner of the restaurant wants to increase the number of different three-course dinners that can be ordered. She will either add one starter, or one main course, or one dessert to the menu. Which should she add to make the number of different three-course dinners that can be ordered as large as possible and justify your answer fully? So we need to actually do out all of them to see which would work. So if we decided to put in an extra starter, we had 4 starters, so it would change to 5. So you'd multiply 5 by the total of main courses, which would stay the same, which would be 5, multiplied by the number of desserts, which would stay the same, which is 3. Now, if you multiply those together, you get 75 dinners. Now, if we put in an extra main course with the original numbers for the other ones, so the number of starters was 4. Remember, we're changing the number of main courses to add one more. This would be 6, and we're not changing the desserts. So 4 by 6 by 3, that would give you 72 dinners. And finally, if you put in an extra dessert, so we wouldn't be changing the number of starters, that would be 4. Multiply by the number of main courses, that's 5. And then if we put in an extra dessert, that would change to 4. Now if you multiply those together, you get 80 dinners. So from that, the combination, or what we should add to make the number of different three-course dinners as large as possible, is 80 dinners, so it's going to be an extra dessert. So you really need to do these out to make sure that you're able to justify your answer. And that's the end of that question. I think I have another one here. I do. So this is 2013. Paper 2, question 7. Now this question is actually bringing in Venn diagrams into probability, so that's where they overlap. So let's have a look. In a survey, 54 people were asked which political party they had voted for in the last 3 elections. The results are as follows. So 30 had voted for the Conservatives, 22 had voted for the Liberals, and 22 had voted for the Republicans. 12 had voted for the Conservatives and the Liberals, 9 had voted for the Liberals and the Republicans, 8 had voted for the Conservatives and the Republicans, and 5 had voted for all 3 parties. Represent this information on a Venn diagram. Okay, so we need to draw our 3 circles. And we're going to draw a box around it as well. Now we're going to label our circles, so this is going to be the Conservatives, the Liberals and the Republicans. So we'll start off with this number here. 5 had voted for all 3 parties, so we're going to put 5 in the intersection part of all 3. Now let's work backwards here. So we were told that 12 had voted for the Conservatives and Liberals. So I'm just looking at this bullet point here. 12 had voted for the Conservatives and Liberals. Now, you need to take the middle part, or the middle number, away from 12, because that includes the intersection bit. So I'm just going to do that calculation over here. So you had 12 that voted for the Conservatives and Liberals, but you need to take away the middle intersection bit. So 12 take away 5 will give you 7, and that's where we put 7 there. Okay, if we look at the next piece of information, 9 had voted for the Liberals and the Republicans. So 9, take away the middle part, which is 5, is going to give us 4. So 4 is going to go in the intersection bit of the Liberals and Republicans. And finally, 8 had voted for the Conservatives and the Republicans. So we've 8, take away the middle part, which is 5, and you're left with 3. So 3 is going to go into the intersection part for the Conservatives and the Republicans. So now we have to look at what's left. So we were told that there were 30 that had voted for the Conservatives in total. So if we look at the whole Conservative circle, so I'm just going to highlight it here. So we're looking at everything that's in the Conservatives, and we're going to take it away from 30 to give us our remainder. So it's going to be 30. I'll do the calculation over here. So 30, take away 7, take away 5, take away 3. And when you do that on the calculator, you'll get 15. So 15 goes here. Then if we look at, let's use a different colour here now, the liberals, so everything that is in this circle here. So we're told the liberals is 22. So that calculation, so it's going to be 22 minus 7 minus 5 minus 4. And when you put that into the calculator, you'll get 6. So I'm going to put 6 in here. And then finally, our last circle that's left is the Republicans. So it's this circle here I'm looking for. And this time we are told that 22 had voted for the Republicans. So it's going to be, so 22 again. So 22, take away everything that's in the purple circle there. So 22, take away 5, take away 3, take away 4. And when you put that into the calculator, you will get 10. So we put 10 here. Now, we are told that 54 people were surveyed in total. So we need to just double check, do we have 54 people accounted for there in the 3 circles? So if you add everything that you see there, 10 plus 4 plus 5 plus 3 plus 6 plus 7 plus 15, you actually get 50, which means that there's 4 unaccounted for. So that must mean that you had 4 people that didn't vote for Annie. And that's the Venn diagram done. So I'm going to move down now. If one person is chosen at random, what is the probability that the person did not vote in any of the 3 elections? Well, we've already figured out that 4 people didn't vote for Annie. Now, out of the 4, how many were surveyed or how many were asked is 54. So 4 out of 54, if you put that into the calculator, you get 2 out of 27. So that's the answer to part B. The answer to part C, if one person is chosen at random, what is the probability that the person chosen voted for at least 2 parties? So at least 2 parties. You're talking about what's in the middle. So all of the intersection bits is at least 2, if not 3. So that's going to be 3 plus 5 plus 7 plus 4. And that's out of 54. So what I've done there is I've added all of the intersection bits because they all account for 2 people who voted for 2 parties or more, which is all 3, which is the middle part. Now when you put that into the calculator, you will get 19 out of 54 and you can leave it as a fraction. So let's look at part D. If one person is chosen at random, what is the probability that the person chosen voted for the same party in all 3 elections? So what is the probability that the person chosen voted for the same party in all 3 elections? So we're going to add together all of the people that voted for one party only. So that would be 15 plus 6 plus 10. So I'm just going to add them together. So it's going to be 15 plus 6 plus 10. And again, it's out of a total of 54. So if you put that into the calculator, you will get 31 out of 54. So that's it. They are kind of the style of questions that you will get asked for probability, and as you can see it overlaps there with sets. So I'm going to attach some useful links and extra video tutorials in the chat, and I'd highly recommend that you follow them as well, and I will speak to you next week.